Hello. Today we're going to talk about an extremely important part in geometric optics of ACT physics. Um, Let me introduce lenses and mirrors. So, briefly, lenses use refraction to change the way an object appears. When light traveling in air enters the denser lens, it slows and bends due to refraction. When it exits the lens and moves back into air, the light speeds up and experiences a second refraction. The type and degree of curvature of the two lens surfaces dictate where the image will appear and how it will be magnified. And for mirrors, we're gonna specifically talk about spherical mirrors. So spherical mirrors are simply small sections of a single sphere that have a reflective surface. First we're gonna talk about convex lens. So in the figure, it demonstrates the symmetrical and spherical nature of a simple convex lens. Although the diagram appears to be two circles, the lens is actually formed by the intersection of the two spheres. The optical axis is a horizontal line running through the center of the lens. All vertical measurements are made from the optical axis. A vertical line, usually not drawn, also passes through the center of the lens. All horizontal measurements are made from the center of the lens. Um, Two key points F and 2F are shown on both sides of the lens. The symbols F and 2F also represent distance measured from the center of the lens to these key points. The point 2F is at the center of curvature of each sphere. The distance 2F is therefore equal to the radius r. As a result, the focal length f can be calculated as follows. So 2f equals r, so if we rearrange this, we can get f equals 2r/2. This means that the focal point f is located midway between the center of curvature and the surface of the lens. The lenses are considered so thin that they have negligible thickness, so not as shown on the graph. So the lens is actually, their thickness is actually negligible. As a result, the focal distance is measured from the center of the lens rather than the lens surface. So let's talk about convergent convex lens ray tracing. Convergent lenses bring light together. So the convex lens is a convergent lens. The location and size of the image formed by a lens or mirror can be plotted using ray tracing. In ray tracing, an object is represented by a vertical arrow extending upward from the optical axis, as shown in the figure. Two different light rays, both starting at the top of the object, tip of the vertical arrow, as you can see, are drawn moving through the lens. Where they intersect is the location where the image will be focused. So there are three main key concepts in rays of tracing. So first, light parallel to the optical axis converges on the far focal point. And second, light that passes through the center of the lens moves in a straight line. And third one, light passing through the focus axis parallel to the optical axis. So this figure shows these three key rays of light originated at the object and intersecting at the image formed by this converging convex lens. And convergent optical instruments, such as the convex lens, in the figure have a positive focal distance. When the object is positioned outside of the focal point f, the image will be inverted and real. For example, movies are projected on a screen, therefore they are real images and inverted. In order to show a movie upright in the theater, the film must be fed into the projector inverted. And there's a key geometric relationship between the focal length f of the lens, the object distance dO, and the image distance di. 1 over f equals to 1 over dO plus 1 over di. All of these variables are in the denominator, as you can see, and it requires a value to be inverted during the solution process. For example, when solving for f, the answer for 1 over f will be one of the available choices. After solving for 1 over f, remember to invert to find f. And on the right is the magnification formula and design conventions. In the table below, it summarizes the signs for the variables and the equations shown above. So some of the tips and strategies you may use in SAT physics exam. So problems on the exam may simply address trends as the object is moved either toward the focal point or away from the focal point. For the convergent convex lens, remember the following points. First one, object outside of 2f, it will create a smaller image, meaning that the coefficient of magnitude will be less than 1, and it will be inside 2f on the far side, and bigger than f, smaller than 2f. And second one, object at 2f, image and object are the same size, meaning that the coefficient of magnitude is 1, and at 2f, right at 2f on the far side. And 3, object between 2f and f, it will create larger image, meaning that the coefficient of magnitude is larger than 1, and it will appear outside of 2f on the far side. And 4, as an object moves toward f, the distance and the image size will increase, generally speaking. And here is the simulation.